The Rutherford model of the atom was an improvement over previous models, but it was incomplete. It did not explain how the atom's negatively charged electrons occupy the space surrounding its positively charged nucleus. After all, it was well known that oppositely charged particles attract each other. So what prevented the negative electrons from being drawn into the positive nucleus? So we're about to introduce a new model, the next step in the history of atomic theory. But remember, each time there's new data generated, the model has to change. So what is the new data here? In the early 20th century, a new atomic model evolved as the result of investigations into the absorption and emission of light by matter. The studies revealed an intimate relationship between light and an atom's electrons. This new understanding led directly to a revolutionary view of the nature of energy, matter, and atomic structure. At the end of this video, I want you to be able to explain the mathematical relationship among the speed, wavelength, and frequency of electromagnetic radiation. Let's start with the properties of light. Before 1900, scientists thought light behaved solely as a wave. This belief changed when it was later discovered that light also has particle-like characteristics. Still, many of light's properties can be described in terms of waves. A quick review of these wave-like properties will help you understand the basic theory of light as it existed at the beginning of the 20th century. Visible light is a kind of electromagnetic radiation, which is a form of energy that exhibits wave-like behavior as it travels through space. Other kinds of electromagnetic radiation include X-rays, ultraviolet and infrared light, microwaves, and radio waves. Together, all forms of electromagnetic radiation form the electromagnetic spectrum. The electromagnetic spectrum is represented in this figure, which is figure 4-1 on page 92 of your textbook. All forms of electromagnetic radiation move at a constant speed, about 3.0 times 10 to the 8th meters per second, represented as m over s, through a vacuum and at slightly slower speeds through matter. Because air is mostly space, the value of 3.0 times 10 to the 8th meters per second is usually considered light's approximate speed through air. Now, a significant feature of wave motion is its repetitive nature, which can be characterized by the measurable properties of wavelength and frequency. Wavelength, represented by the Greek letter lambda, is the distance between corresponding points on adjacent waves. Depending on the particular form of electromagnetic radiation, the unit for wavelength is the meter, centimeter, or nanometer, and 1 nanometer is 1 times 10 to the negative 9 meters. As shown in figure 4-1, right there, frequency, represented by the Greek letter nu, is defined as the number of waves that pass a given point in a specific time, usually 1 second. Frequency is therefore expressed in units waves per second. Now, 1 wave per second is called a hertz, represented by capital H lowercase z, named for Heinrich Hertz, who was a pioneer in the study of electromagnetic radiation. Figure 4-2 in your textbook illustrates the properties of wavelength and frequency for a familiar kind of wave, a wave on the surface of water. Now, the wavelength in figure 4-2, that top figure, has a longer wavelength and a lower frequency than the wave below it. So we see that the distance between any two corresponding points on one of these water waves, such as from crest to crest, is the wave's wavelength, lambda. And we can measure the wave's frequency, nu, by observing how often the water level rises and falls at a given point, such as the post. So frequency and wavelength are mathematically related to each other. For electromagnetic radiation, this relationship is written as follows. C is equal to lambda multiplied by nu. In the equation, c is the speed of light, lambda is the wavelength of that electromagnetic wave, and nu is the frequency of that electromagnetic wave. Because c is the same for all electromagnetic radiation, the product of lambda times nu is a constant. Consequently, we know that lambda is inversely proportional to nu. In other words, as the wavelength of light decreases, its frequency increases, and vice versa. So, hopefully you can explain the mathematical relationship among the speed, wavelength, and frequency of electromagnetic radiation.